Hello and welcome to this e-seminar which will provide an introduction to digital PCR. This e-seminar will introduce you to the digital PCR technique and provide recommendations, guidance and best practice for the application of the technique for routine testing purposes. It is assumed that you have a working knowledge of both PCR and quantitative PCR. However, if you require further information, please refer to the 2013 publication Good Practice Guide for the Application of Quantitative PCR by Nolan, Huggett and Sanchez, which is free to download at the URL displayed at the bottom of the slide. In the following section, we will provide an introduction to the digital PCR technique, give examples of applications to which it can be applied, mention some advantages and limitations, and give examples of the platforms and instruments currently available commercially. The digital polymerase chain reaction is an adaptation of the basic PCR method, which can be employed for determining the absolute copy number of a DNA target. The technique is based on the concept of limiting dilutions. If a dilute, homogeneous solution of DNA targets is partitioned into a large number of reactions, some of the reactions will not contain any target molecules. Post-PCR reactions can be classified as either positive, target detected, or negative, target not detected, thus providing the basis for a digital output. By applying Poisson statistics to the results obtained, an estimate of the number of target molecules present in a test sample can be calculated. The digital PCR technique is based on a number of key assumptions. Firstly, that the DNA targets are distributed homogeneously within the test sample, such that when aliquoted into a large number of identical partitions, some of the partitions will contain one or more than one DNA target. Secondly, that provided the distribution of DNA targets between the partitions is independent and occurs at a fixed rate, the distribution of DNA targets across the partitions will be Poissonian. And thirdly, that provided the distribution of target DNA molecules is Poissonian, the average number of targets present in each partition can be estimated by applying the equation illustrated, which states that lambda equals the negative of the natural logarithm for the number of negative partitions counted, divided by the total number of partitions counted. The result for lambda can then be converted to a concentration by taking into account the total volume of all of the partitions employed in the equation. Digital PCR is particularly useful where the validity and precise determination of a target molecule is essential. Examples of applications where digital PCR may be used include the detection of undeclared ingredients and genetically modified organisms in samples of food and feed, the determination of viral load and detection of residual disease in medical-based analysis, and assigning DNA copy number values for certified reference materials. The digital PCR technique has a number of potential advantages and limitations for the quantification of DNA targets, compared to approaches based on conventional quantitative PCR methods. One advantage is that it provides a method for estimating the absolute DNA target copy number of a test sample without the requirement for a calibration curve. It can also provide results with a high level of trueness and precision. Finally, the technique has been reported to be less sensitive to the effects of PCR inhibition on quantification, which enables the detection of rare targets in complex backgrounds. A potential limitation of digital PCR is that the cost of instrumentation, consumables and reagents can be more than existing methods. The dynamic range of the analysis is also smaller than that for conventional quantitative PCR approaches. In addition, current digital PCR workflows can be more complex, and the time required for setting up and analysing experiments can be longer than quantitative PCR. It is difficult to estimate the additional costs associated with using digital PCR when comparing it to conventional quantitative PCR approaches, as this is dependent on a number of factors. These include the price of instrumentation and associated maintenance costs, the additional costs of purchasing digital PCR-specific consumables and reagents, the level of precision and sensitivity required, the level of sample throughput, the complexity of the workflow, and the length of time required to analyze the data. However, there are also cost savings associated with not requiring a standard curve. If you are considering establishing a digital PCR capability, then implementation of a careful evaluation of the cost benefits for adopting the technique is recommended. Digital PCR utilizes many of the reagents common to performing conventional quantitative PCR. However, certain key components and reagents are frequently platform or instrument specific and need to be taken into account when determining the likely operating costs of an instrument. These items may include specialized chips, for example, Fluidigm integrated fluidic circuits, cartridge gaskets, for example, Biorad QX200 cartridge gaskets, and platform-specific instrumentation, for example, Biorad droplet generator. There are two main approaches for performing digital PCR: chamber-based methods, abbreviated as CD-PCR, and droplet-based methods, abbreviated as DD-PCR. Chamber-based approaches utilize arrays of prefabricated solid-state partitions, where the number of partitions employed is both fixed and consistent between experiments. The approach typically employs dedicated thermal cyclers which enable partitions to be cycled and read. Although the number of partitions is generally lower than for droplet-based platforms, the approach is associated with simplified workflows. Droplet-based approaches partition the PCR reaction mix by emulsification of the aqueous mixture in oil. The droplets can then be thermally cycled in standard PCR tubes, strips or plates, and the endpoint droplet fluorescence measured using a dedicated reader. Compared with chamber-based digital PCR approaches, the number of partitions generated is greater, but can be different between experiments and instruments. A number of chamber-based digital PCR instruments are currently commercially available. These include the Biomark HD system from Fluidigm, the Quant Studio 3D system from Thermo Fisher Scientific, the Constellation system from Formulatrix, and the Clarity Digital PCR system from JN Medsys. The table presented on the slide summarizes some of the key features associated with examples of chamber-based instruments. A number of droplet-based digital PCR instruments are also commercially available. These include the QX200 droplet digital PCR system from Biorad, the Raindrop digital PCR system from Raindance Technologies, and the NICA system, Crystal digital PCR system from Stilla Technologies. The table presented on the slide summarizes some of the key features associated with examples of droplet-based instruments. In the following section, we will provide some general guidance for consideration when designing digital PCR experiments and analysis of the data generated. The digital PCR reaction setup is similar to that used for quantitative PCR, the key difference being the process of partitioning of the PCR reaction mix into large numbers of individual reactions known as partitions. A typical digital PCR master reaction mix has a number of components. It will contain a DNA template, which should have an A260 to A280 ratio of 1.8, an A260 to A230 ratio of 2.0, and be at a concentration for double-stranded DNA sufficient to theoretically generate a value for lambda, target copies per partition of 1.6. The mix will also contain forward and reverse oligonucleotide primers. a hydrolysis probe is included, except where an intercalating dye approach is employed. However, the choice of quencher is restricted with some platforms. It is strongly recommended that any guidance provided by the instrument manufacturer on the selection of fluorophores and quenchers be referred to. An appropriate PCR master mix is required. The exact composition of proprietary digital PCR master mixes is not always disclosed, so an assay's performance should be evaluated through the use of certified reference materials where available. Finally, the reaction mixture should be adjusted to the appropriate volume with the addition of nuclease-free sterile water. The thermal cycling profiles employed with validated quantitative PCR methods have been reported to be generally transferable to digital PCR platforms without the need for additional optimization. However, the exact thermal cycling conditions used in practice are dependent on the platform and instrument that is being employed. Where secondary targets are detected, it is recommended that an annealing temperature gradient evaluation is performed. However, where additional optimization needs to be performed, revalidation of the method may be required before it can be employed for analysis. Some platforms have specific thermal cycling requirements. For example, droplet PCR systems may require a final cycling step at an elevated temperature in order to stabilize the droplets. In addition, many platforms specify specific thermal ramp rates in order to ensure uniform heating of the partitions is achieved. Finally, it is recommended by the European Union Reference Laboratory for GMOs in feed and food that a minimum run length of 45 cycles is adopted. This may aid in obtaining adequate separation between background and positive signals, which can assist in accurately classifying partition reaction status. The scoring of the reaction partitions post-thermal cycling is the first step in the digital PCR data analysis process. Scoring is based on the level of post-amplification fluorescence detected. This requires a signal intensity threshold to be set in order to determine which partitions represent a positive result and which represent a negative result. Ideally, the fluorescent threshold should be placed midway between the average fluorescent amplitude determined for the reaction positive and reaction negative partition clusters. This threshold should then be applied to the scoring of all of the partitions that are to be analysed. For the purposes of preliminary quality screening of digital PCR data, there are a number of recommendations on when a dataset may be rejected. These include when the total number of partitions analysed drops below the platform critical threshold recommended by the manufacturer, when the average fluorescent amplitude of the positive or negative partitions are clearly different from those obtained for other wells or inlets, or when more than 5% of the accepted partitions have a fluorescent value below that of the negative cluster. The following guidance may prove useful in designing and analysing digital PCR experiments. As a general rule of thumb, it is recommended that at least 2 subsamples are taken from the laboratory sample and that dual DNA extractions are performed on both. Digital PCR should then be performed on each of the extracted test samples and the results averaged across the multiple repeats. Confidence intervals should be calculated using the standard deviation derived for the pooled data. When considering the optimal DNA target concentration to employ, the double-stranded DNA concentration of the test sample should first be determined using an appropriate method. For example, the Quant-IT Picogreen DSA DNA assay kit from Thermo Fisher Scientific. The template should then be diluted appropriately in order to generate a theoretical value for lambda, the target copies per partition of 1.6. Finally, it is useful to establish the level of compartmentalization that has been achieved by the experiment, as this will determine the sensitivity that can be obtained. For example, To detect a DNA target present at the 1% copy number per copy number of abundance, at least 30% of the sample will need to be partitioned. For the Bio-Rad QX200 platform, this equates roughly to a minimum of 7,000 partitions of a possible 20,000 partitions. To detect a DNA target present at the 0.5% copy number per copy number of abundance would require at least 50% of the test sample to be compartmentalized. As a consequence of reaction partitioning, the presence of non-specific amplification products can be more easily detected. In the upper figure presented here, a second population of partitions is visible below the main positive cluster. In the lower figure, a second population of partitions is visible above the negative cluster. Non-specific amplification products typically have a lower endpoint fluorescence signal when compared with a primary target, and can be visualized as additional partition populations with fluorescence signal values between those of the primary target and the negatives. Importantly, the presence of multiple partition populations may complicate analysis of the data by influencing the positioning of the cutoff threshold, which may lead to the misclassification of scored partitions. Potential causes of specificity issues include non-specificity of the assay and spectral overlap. Non-specificity is where the primers and/or probe anneal to DNA sequences other than the primary target. This may occur when pseudogene sequences are present, or, alternatively, and particularly in plants, where duplicated regions of the genome exist. Spectral overlap is where an overlap in the emission spectra exists between assay fluorophores, which may lead to signal bleed through from one assay's detector to another. A number of strategies exist for dealing with assay specificity. Additional assay optimization may be performed, primarily through analysis of primer and probe annealing temperature effects and the use of temperature gradient evaluation. Alternatively, the assay could be redesigned to be more specific, although this would require revalidation of the assay to be performed. Finally, possible spectral overlap of the fluorophores may be reduced by employing narrow emission reporter dyes. The figure presented here illustrates the impact of increasing the annealing temperature on PCR assay specificity, which has resulted in the reduced amplification of a secondary target. Following preliminary analysis of the results, a number of digital PCR-specific criteria may be applied to evaluate the quality of the data generated. These include establishing that the assay has amplified only a single target, which has resulted in the generation of two distinct, positive and negative partition populations, and determining that sufficient separation between the signals of the positive and negative partition clusters has been achieved. The latter is commonly referred to as peak resolution and is discussed in more detail later in the presentation. Finally, the fraction of partitions which possess intermediate fluorescent value, otherwise known as RAIN, should be checked to confirm it does not exceed 2.5% of the total number of partitions accepted for analysis. RAIN, or drag, is the term applied to partitions that exhibit an intermediate level of fluorescence that falls between that for the positive and negative populations. Examples of RAIN are shown in the figures on the slide. The RAIN appears as dispersed partitions which are located between the two main partition clusters. Some RAIN can be attributed to the late onset of PCR, and should therefore be considered a member of the positive partition population. As a consequence, a certain level of RAIN may be considered acceptable as an integral component of any digital PCR experiment. Mathematical simulations have demonstrated that up to 2.5% of the counted partitions can be tolerated as RAIN before a 25% quantitation bias is exceeded. Therefore, it is recommended that a threshold for RAIN be established as 2.5% of the partitions counted and scored. datasets which exhibit rain in excess of this threshold should be considered as unreliable. A number of recommendations have been presented for dealing with excessive levels of rain. Firstly, it is important to determine if a significant proportion of the rain is the result of late amplifying partitions. This can be determined by systematically increasing the number of cycles in progressive increments from the standard 45. If the level of rain is significantly reduced by increasing the number of cycles, then the threshold should be positioned as close to the negatively scored population of partitions as possible. Alternatively, the rain may be caused by the mispriming events of the primers and probe. This can be evaluated by performing an annealing temperature gradient analysis on the primers and probe, which may identify an alternative annealing temperature that reduces the existing rain component. An example of the results for an annealing gradient experiment is shown in the top figure. The use of an annealing temperature of 62.2 degrees centigrade can be seen to greatly reduce the rain component. A further option that has been reported to help with excessive rain is to fragment the DNA using a restriction enzyme that cuts outside of the primer and probe sequences. An example of the results obtained for reducing rain by restricting template DNA is shown in the lower figure. A more recent strategy has been the introduction of dual-quenched hydrolysis probes, which in certain cases have been reported to help reduce levels of rain. Details regarding the use of dual-quench probes is beyond the scope of the current e-seminar. Further information can be found in a 2017 publication by Collier et al., which covers the subject in more detail. Peak resolution refers to the degree of signal intensity separation observed between populations of partitions. This can be thought of in terms of signal peak resolution and can be described by the equation shown on the slide. The value derived for RS takes into consideration the absolute fluorescent intensities obtained, the distribution of intensities, and the degree of overlap present for the both clusters of partition data points. It has been recommended that an RS value of 2.0 be employed in evaluating the quality of the data generated by a digital PCR experiment, as this ensures that clear separation between partition clusters has been obtained. For further information regarding the technique of DPCR, see the list of publications on the slide and the Digital PCR section of the Gene Quantification website at the URL www.gene-quantification.info. We would like to acknowledge the support received in preparing, delivering and funding this e-seminar, in particular the Department for Environment, Food and Rural Affairs, the Government Chemist Programme for 2017 to 2020, the Department for Business, Energy and Industrial Strategy, the Food Standards Agency and Food Standards Scotland. And finally, we would like to thank you for your attention.